Just like yesterday, I'll start with a presentation of the Bitcoin integration. So I'll talk about Bitcoin and how it works under the hood with the ICP integration. And then Jordan will do examples with Hazel. So it's about Bitcoin and the fact that the internet computer is integrated with the Bitcoin network. Usually, when you want to move funds between ecosystems, it has always been a huge problem in crypto. So we know a lot of different blockchains. We have Bitcoin, Ethereum, Solana, Cardano. We have a lot of different ecosystems. And the problem is that once you are in one ecosystem, it's very hard to communicate with other ecosystems. So essentially, contracts and funds in one ecosystem, they are not natively able to communicate with other ecosystems. So there is the concept of a bridge, which has been around for a long time, and it's essentially trying to solve the issue. How it works? Well, let's imagine that we are the person in the middle here. We have Bitcoins, so we have Bitcoins that are living on the Bitcoin network, but we would like to use them for some DeFi applications on Ethereum. So I've listed some of them, for example, Uniswap or Curve, which are essentially smart contracts deployed on Ethereum. And so we cannot just use our Bitcoins on the Ethereum network because they don't have a meaning, they don't have an existence. And the way it works, it's essentially you have a wallet on the Bitcoin network where you need to send your Bitcoin. This wallet is controlled by an entity, and this entity also controls a smart contract on Ethereum, which is called wrap Bitcoin. And essentially, when you send the Bitcoin, it's going to create a wrap Bitcoin, and you can use the wrap Bitcoin on Ethereum. So you can put them inside contracts of Uniswap and Curve, and you can enjoy your Bitcoins. The problem with that is we have no guarantee that the entity is not going to create more wrap Bitcoin than they have Bitcoin. Essentially, they are supposed to always keep a 1-1 ratio so that you can always get back your Bitcoin. But we know what can happen in some circumstances. So there has been a lot of hacks, either due to wrong code, so bridges that were hacked, or just people stealing funds. So it's not the best solution. It introduces a centralization point. And that's why on DIC, we have a different solution, which is native. So it's essentially integrated into the protocol. What it means is that on the internet computer, canisters can receive, hold, and send Bitcoins. So a canister has an address on the Bitcoin network, like any other user or any other wallet. And a canister is able to sign and broadcast transactions to the Bitcoin network. So essentially, the two networks are connected. It's very easy for developers to use, as we'll see later. And the fact that we have this native integration enables, I would say, way better security because it's less clunky. It's like it's not perfect. There are some security assumptions that we'll talk about, but it's essentially a better approach. So how it works exactly? Essentially, you have the ICP network on the left and the Bitcoin network on the right. Let's imagine that you have the Bitcoin nodes on the Bitcoin networks and you have the ICP nodes on the ICP network. The ICP nodes are connected directly to the Bitcoin nodes. And they are essentially syncing the Bitcoin blockchain. So they are keeping track of what's happening on the Bitcoin network. Also, there is a Bitcoin canister on the IC, which is essentially a replication. So like an on-chain version for the Bitcoin on the ICP, there is a canister called Bitcoin canister, which store the ETXOs and the balances of the Bitcoin wallets and addresses. And this canister is essentially what enables you as a developer to communicate with the Bitcoin network. So you want to get the balance of an address, for example. It's as simple as doing balance is equal await management canister dot Bitcoin get balance, like we did with HTTP outcalls. And you can just call this Bitcoin canister under the hood, which is a replication of the Bitcoin network, and you get informations. There is a second component, which is really, I think, the innovation behind all of this, and it's called threshold ECDSA. So essentially, you are able to sign a transaction from a canister. And I'll explain how it works, just now exactly. So we need to explain what is ECDSA. If you don't know what is the t-ECDSA, it's essentially a very, very famous scheme for creating keys, so public key and private keys. Essentially, you create a private key. With the private key, you're able to create a signature. You keep this private key secure, and you're able to verify the signature with the public key. Anyone is able to verify. That's how you essentially create transactions from, that's how you create transactions for Bitcoin or like any other chain. The problem with that is that we cannot just store this key, like the private key, on the ICP network. So we cannot just give the key to a node, otherwise that would be very, very insecure, and they could just run with the money. So they had to come up with something that is called threshold ECDSA. And so essentially the key is divided into shares, and the shares are shuffled across the nodes. So each node has a share of the ECDSA key. And as a group of nodes, so as a subnet, they are able to go through consensus and create a signature, but they're not able to, as a single node, stole the funds or create a signature. So the private key is never reconstructed, and the shares are regularly shuffled around for better security purposes. And yeah, essentially every time you want to create a signature with your canister, you have to go through an update call, you have to go through consensus, and it's essentially the ICP protocol that makes sure that your key is safe and secure. So if you would to think about, if you think about what it needs to take over this, you essentially need to have 2/3 of the nodes. So, sorry, 1/3 of the nodes. So the security of this is going to depend on the number of nodes in a subnet. If you have 30 nodes, it's going to be somewhat secure. If you have 30 nodes, it's going to be way more secure, and so on. So there are still some security assumptions. We still need to be careful, but it's, yeah, essentially you would need to take over 10 of the nodes, and the nodes are supposed to be independent entities. So you would need to have 10 persons that essentially take over the subnet to steal the funds. And there are way more complication if you go into details, but essentially that's what it is. Yeah, so that's about it. That's how you create a CDSA signature. And once you have that, you essentially can do whatever you want with the Bitcoin network. The second part is this part of connecting with the other network. So we have the nodes, ICP nodes, and they are connected to random Bitcoin nodes. So your ICP nodes, you just look around in the world and you connect to 5 random Bitcoin nodes to make sure that you have enough source of informations. Then you just load the blocks and the transactions. And then it's a bit more complex under the hood, but essentially they just copy what they see into the Bitcoin canister, which is essentially a replication of the Bitcoin blockchain. You don't have all the transactions, but you have all the UTXOs. So UTXOs is what you use for Bitcoin transactions. And once you have that, as I said, you can just, with any canister on the IC, you can just communicate through inter-canister call, and you can get information about your balance. You can create transaction, create signatures, and broadcast transaction. And so when you broadcast a transaction, it's essentially just an ICP node that sends the transaction to a Bitcoin node, and then the rest of the transaction will happen on the Bitcoin network. So that's very, very great. And the owner of the Bitcoin canister is no one. So it's essentially the system. It's the NNS. So essentially it's the IC that is owner of the Bitcoin canister. So we're still able to upgrade it, but only through a vote of the DAO, the NNS, which I've already talked about. There is another component to this Bitcoin integration, and it's called chain key Bitcoin. So it's the token that you can see on the right. The problem with the Bitcoin integration as it is natively, it's that even though canisters can manipulate Bitcoin, they can hold them and send transactions, doesn't solve the problem of the Bitcoin transactions being very slow and expensive. And so if you don't want to wait, you can use chain key Bitcoin, which is a token native to the internet computer. So the ledger is a canister on the IC. It's completely transparent, so the code is open source, and I'll explain how it works. It's backed 1-1 by real Bitcoins. 2-second transactions, like transactions on the IC. And you can easily integrate with any service on the IC because it's following the ICRC1 standard, the one you're working with. And it's essentially a few lines of code to get a payment system with that. So yeah, it's a ledger canister like the ICP ledger. It's not the same, but it's another canister that is a ledger. And it's a ICRC1 type of ledger. To make sure that there is always one Bitcoin corresponding to one chain key Bitcoin, essentially you have two canisters. The first one is the minter. The minter is able to create chain key Bitcoin or burn chain key Bitcoin. And the minter has a Bitcoin address on the Bitcoin network. So it's like the bridge we've seen before. You send your Bitcoin to an address, then the minter will check, is there a Bitcoin on the address? Whenever it's sure that it has received your Bitcoin, it will send a notification to the ledger and it will create one chain key Bitcoin. In the meantime, you don't have access to your Bitcoin. But if you want to get back your Bitcoin, you just send the chain key Bitcoin to a specific address and you get back your Bitcoin. It's essentially the same principle than a bridge. The only difference is that instead of having a corporation or a set of corporations that are responsible for making sure there is always one-to-one ratio, you have to trust canisters. And so the code for those canisters is open source. You can find it on GitHub. You can also check that is the code that is running on the IC. And once again, the controller of those canisters is the NNS. So you're essentially subject to less risk in a sense because it's software and fully transparent software. Once you have the Bitcoin that is the chain key Bitcoin that is on the ICP network, it's very easy to interoperate with any application. So for example, OpenChat, just a single intercanister call. You have your OpenChat canister that will call the chain key Bitcoin ledger to do a transfer. And you can use it for sending money to people directly on any ICP application. So it's very, very easy to integrate as a developer and very easy to use as a user. Yeah, I'm sending, not receiving, unfortunately. So the use cases, yep. The use cases, there are some, but I think we can, yeah, I've listed some of them, but it's not like accurate list. There are probably way more. The first one is Socialify. So it's the mix between social application and financial application. We'll see more and more ways to send money easily or borrow money easily. You can also have on-chain exchanges. So essentially trying to decentralize what are Kraken and Binance. You can replicate those exchanges on ICP. And so you don't have to trust a company. You can assign the control of this to a DAO once again. Chain key Bitcoin, I've already talked about that. So 2 seconds transaction for Bitcoin. You also have crowdfunding. So there is a platform called Funded on the IC where you can invest early in projects using Bitcoin. There are ordinals. So Bionic is an ordinal marketplace that is released pretty soon, I think. And yeah, essentially they are using the Bitcoin integration to do very, very fast and very, very cheap ordinals transfers. And the last one that I've listed is Finterest, which is a lending protocol. So you can put your Bitcoin to work. Essentially right now, most people that have Bitcoin, they're just holding them, not benefiting from any kind of interest or yield. And so you can put it inside an application, which is controlled only by canisters. So you don't have to trust someone, you just trust the canisters, and you can receive an interest on that. So yeah, that's essentially the Bitcoin integration. It has been released, I think, end of the year, so December 2022. I think it took a long time, like almost 1 year of engineering to come up with this integration. It has trade-offs like any other innovation. But as far as it stands right now, it's one of the best way to bring smart contracts to Bitcoin and also more utility to the Bitcoin network. And so the interest, like the role of doing all of this is that there is a lot of liquidity. liquidity in the Bitcoin ecosystem. But this money is not very used and very useful because it's not put into DeFi application, or it's not really put to work. And so, yeah, that's the goal of the Bitcoin integration, is to bring this liquidity on the Bitcoin, on the ICP network. And there are way more projects that you could work on, for example, Bitcoin wallets on ICP and other kind of DeFi application. There is a list of them, and I'll provide that on day 7 if you have some ideas you want to build around. Okay. Over to you, Jordan.
Okay, now how do you program this? So today we'll be going into the ASL book reference section 20.1 Bitcoin. This just gives you a bunch of links to all the resources. So there's a few key components, and Seb went over most of them, but basically there are two main ways to interact with Bitcoin on the internet computer. One is going to be the direct Bitcoin integration. That means that you are using threshold ECDSA to sign Bitcoin transactions, and then you're using the Bitcoin management canister methods to interact with the Bitcoin network, submit transactions, get UTXOs, etc. So that's the direct integration. And then there's the CKBTC, which is just another token. Some people say it's not wrapped. It's a wrapped token. The CKBTC canister, in my opinion, is the wrapper, but it uses under the hood the threshold ECDSA and Bitcoin integration to get those Bitcoins into that ledger canister, basically. So we'll just go over the basics of how you deal with all these things. So first step is threshold ECDSA. So ECDSA is I guess you could say, a signature scheme, right? It lets you generate public and private key pairs. And like Seb was saying, on the internet computer, and because it's threshold, the private key is never stored in one place, right? And it's very easy to do this. So the API looks like this. So you just import the management canister, just like we've always done. And then if you want to get a public key, you just call .ecdsa public key on the management canister. And right here, the derivation path. This is how you can derive a number of private keys or a number of key pairs for your one canister. Sure, your one canister, basically as a developer, you are building an application that can control private keys. Imagine Coinbase or some other exchange where they actually have your private key pairs. The difference is this is threshold. On Coinbase, they actually have one private key that they're storing securely and everything. Like generally to sign transactions, they would need to go retrieve a key pair and bring it back and deal with that securely. So you are basically being the back end of one of these big companies. The derivation path will let you pass in some path that would let you change that key pair basically based on what you want. So a really easy way to think about it is, imagine if you just want to have one key pair per user, then you could just grab the caller. The caller is the principal of whoever called, right? So the user is going to have a key pair on their device if they log in with internet identity or some other mechanism, right? And when they sign in and then call into this method, caller will be their principal. So you can just turn that into a uint data array, boom, and you can just pass that in as derivation path. Now you'll have one key pair per user. Well, imagine you want more key pairs per user. Well, then I suppose you could take the caller and maybe have some index, right? So you could combine, you could combine this principal, maybe turn into a string, add a dash, add a number, or do some kind of other thing, right? And then you pass in your key ID, which just tells you like which key you want and which signature scheme. I believe right now all we have is SecP256K1, so I think that's just the main ECDSA key. And then the name would be, I guess whether it's test or production. this is all for the test material. So if you're going to do it in production, you have to grab the production key name. I don't remember what that is, but you can always go to the official documentation at internetcomputer.org, and I imagine it will have the information there for you. Okay, once you do that, you just call it just like everything else. It'll do an asynchronous request and come back and get you a public key result. You can match on that, and what's inside? What do you know? A public key. Pretty cool. So that's just generating a key pair basically and giving you the public key. And then there's signing with the key pair. Signing is also very, very simple. Basically, you pass in a blob, or it's a uint array, right? You pass in a uint array of the data that you want to sign. So this would be your Bitcoin transaction or your Ethereum transaction or whatever you want. This is not the ECDSA APIs are not specific to Bitcoin and Ethereum. It's any ECDSA application that you want. So let's pretend though this is a Bitcoin transaction that you've already created elsewhere, and now you've turned it to bytes. Okay, we are going to go retrieve the public key for this user. Well, we're not going to retrieve the public key. We're going to tell it, hey, use the public key at this derivation path, right? And then we'll pass in our message hash, and then we'll pass in the key that we want. You have to pay for it. We talked about in where did we? I think yesterday we did talk a lot about cycles. Yeah, with HTTP requests and such. So some APIs require you to pay, and so you got to tack on your cycles. So yeah, you'll execute this. It'll be asynchronous. Boom. Come back with the signature result. If there's an error, you'll get the error. But if there's not an error, you will have your signature here, which is really cool. Let me show you the actual TypeScript types for this under the hood. So if we go to the threshold ECDSA example, let me get these types in here for you. Okay, so for the signing with ECDSA, if we go look at this method, we already went over the args, but the return, okay, it's just a signature, which comes back as a uint data array. So you pass in a message hash, the signature, you'll get back a signature as a blob. And yeah, this is sufficient to build Bitcoin type applications on top, which is pretty cool. Okay, that is signing with threshold ECDSA. This is the first key building block. And I believe this is it. There's just these two methods: generate the key pair and then sign. Let me pause here. Are there any questions about this? You need to understand this piece to fully understand the rest, I would say.
There is no question so far.
Okay. So next is dealing with Bitcoin itself. Okay, and again, so far this is all the native Bitcoin integration. This is not the CKBTC ledger canister. How do you do? Okay, so imagine you have a signature, right? Now, how do you actually interact with the Bitcoin blockchain? Well, you have a number of methods, again, on the management canister that are going to let you deal with the Bitcoin blockchain. So let's go take a look. Remember, these are all in the ASL repo. All these examples are here for you to go look at. So we'll look at the basic Bitcoin example. Or no. The Bitcoin example. Okay. First, we have get balance. So let me just show you. If you go to the management canister, yep, 1, 2, 3, 4. There are 4 Bitcoin APIs. Get balance, get current fee percentiles, get UTXOs, and send transactions. So we'll go over each of those. Okay, get balance is going to do, I think, exactly what you think. You pass in an address as a string. You pass in the minimum number of confirmations that you want before it will I guess grab the balance. So if you set it as none, it's going to grab, I believe, the latest block that it can see. So even if the block was just minted and created, it will go in and grab that balance. I'm going to guess that that's exactly what's going on under the hood there. If you pass in a mint confirmation of, for example, 6, then I think it will ignore the first basically 6 blocks or 5 blocks. I don't know if there might be a plus or minus 1 there. And it will look at the balance with that minimum number of confirmations. And if you're not familiar with confirmations on Bitcoin, a confirmation is basically a block being built on top of your block. And how Bitcoin works is it's using proof of work, and it's probabilistic, right? And it's saying that basically with the more time that passes and the more blocks that are built on top of a transaction, the less likely it's going to be that some malicious miner or group of miners is going to be able to produce a malicious block. So the longer you wait, basically the more secure your Bitcoin transaction or your block is. So you probably wouldn't want to do, it depends on your application, but generally speaking, at least when I was super into Bitcoin before, now I just observe, you would probably want to do probably 6. 6 seems to have been in the past that kind of min confirmation time, which gives, it's basically an hour. So you wait an hour and then generally let people think it's secure. But depending on your application, you might make it more or less. But to just test it, it's easy to keep it none. And then you pass in your network. Basically, if you're on mainnet, you pass in mainnet. And if you're local, you'll do something else. And then you pass in your cycles. Again, you have to pay for it. So we went and determined these costs. I'm not sure if these are the exact costs as they are today. I don't remember the heuristics that we used to get them, but I would recommend you go into the official documentation and try to find out these exact costs. Okay, so that's get balance, and that will return you a balance in Satoshis. Okay, get current fee percentiles. So on Ethereum and on Bitcoin, there are fee markets that basically tell you how much transactions are going to cost, right? And these markets are variable and dynamic. So you don't ever know, there's not like a fixed cost for a Bitcoin transaction. So to help you determine what fee you should use, you can call Bitcoin get current fee percentiles, which is going to return a vector of millisatoshis per byte. And I don't know how many they're going to give you or over what length of time. I assume you can go into the main documentation to find that out. But basically, this is information that is going to help you determine fees. And then get UTXOs. Again, you pass in an address and pass in your network. Get UTXOs result will give you information about UTXOs. And here's what a UTXO looks like. Height, out point, value. I mean, honestly, we've built the API, but I don't do tons of Bitcoin programming. So if you're into Bitcoin, then hopefully you know what all these things are. But this is the API. And I'm not sure exactly what filter does, but it is there for you. And then finally, send transaction. Once you have signed a transaction with ECDSA, this will be your transaction right here, right, as a blob. So you'll calculate your fees. And yeah, so I assume that this is a very simple example, right? So I assume you would want to actually be using the get current fee. The get current fee percentiles is going to be for the Bitcoin fee itself, right? There's a difference between the Bitcoin fee and the cycles fee. So you do need to pay ICP cycles just to get this going. And then whatever Bitcoin key pair you have is going to have the Bitcoin in it to pay for the Bitcoin transaction cost. And then you just say send transaction. So this one is relatively simple. Once you have the correct cycles, you just pass in your transaction with a number. So those are the 4 main APIs. They're relatively simple. Yeah, look at the main documentation to figure out all these things. And if you, this is relatively low level Bitcoin programming, I guess you could say. So yeah, you'll need to understand all that about Bitcoin to get this going. If you want a deeper dive example, the basic Bitcoin example, which we call it basic Bitcoin because I believe that's Dfinity's name for this example. So this is basically a rewrite of Dfinity's Rust example in TypeScript. So it's not more basic than the Bitcoin example, but this goes into more details showing, just a more real example of how this works. So for example, I guess we're using test keys everywhere because this probably wasn't live at the time. Again, this is very simple. Getting the balance, getting the UTXOs, getting the current fee percentiles, getting a specific address type that you need to use, and sending. There's nothing too crazy there. ECDSA, very simple. We're just using the 2 methods that we talked about, right? Those are basically the same. The Bitcoin API, again, I think these are just the 4 methods we talked about again. We're just wrapping them up nicely. Get UTXOs, the current fee percentiles. Oh, cool, we have more information. Returns the 100 fee percentiles measured in millisatoshi per byte. Percentiles are computed from the last 10,000 transactions, if available. So parse that information and use it to determine your fees. And then sending a transaction, nothing crazy there. And then finally, this is the wallet. This is where probably the bulk of the functionality is that you would need to actually build an actual Bitcoin application. So there's this very specific type of address. I believe this is the only address type that the API provides. So, you can go see how we do this. Relatively complicated. Yep. But there it is. Sending. Oh, cool. You can see, the logic for actually dealing with the few percentiles and such. You get your public key, you turn it into your address. You go get the UTXOs for your address. You build up your transaction. Turn your serialize your transaction into a blob. Sign your transaction. Send your transaction. Get the transaction ID. So if you're noticing, it's quite low level. It's relatively complicated. This is like, I guess you would say, true Bitcoin programming. But what's really cool is, as Seth was saying, and I think objectively speaking, the internet computer is not the most popular blockchain, but I feel like it might be the most capable Bitcoin layer 2 that exists right now. And there's nuance to that, but you have the giga level compute resources of the internet computer. You have the threshold ECDSA capabilities, and you can talk to Bitcoin, which is absolutely fantastic. So super low level, and this example is using the plugin API of Azel. So a lot of this code is actually under the hood Rust. So basically we created a lot of these TypeScript types to hook into Rust code, because a lot of these things either don't exist or the npm packages would not work in Azel. And so, we wrote a ton of Rust code to actually expose these libraries. So obviously not the most user-friendly at this point. But if you want to do low-level Bitcoin programming, technically speaking, you do have the capabilities. So that leads us into CKBTC. So let's just talk about, I guess, the trade-offs or the drawbacks even of using Threshold DCA and Bitcoin integration. So obviously Threshold ECDSA and talking directly to the Bitcoin network is going to be the most secure way of interacting with Bitcoin from the internet computer. is going to be the most like Bitcoin native way that maybe wouldn't offend the principles of many Bitcoiners, or at least the loud ones. But it's going to be as slow as the Bitcoin network. It's going to be as expensive as the Bitcoin network. So you're not getting around that core scalability and that core cost of Bitcoin. You are able to do programmatic things with Bitcoin private keys that generally centralized services would have to do with centralized private keys. So that's the main capability there. CKBTC, though, does, with some trade-offs, get around the speed and the cost issues of Bitcoin, because essentially you bridge your Bitcoin in, right? CKBTC will allow you to generate a threshold key pair, and you send your Bitcoin to that key pair. Then, after a certain number of confirmations, the Bitcoin, the CKBTC, set of canisters decides that that is secure enough, and it will mint you a certain number of CKBTC, which is an Internet Computer specific token. Once you have CKBTC on the Internet Computer, you are not bound to the Bitcoin network anymore, except for when you want to come and redeem your Bitcoin. So now you're free to use the cycle cost of the Internet Computer to send your CKBTC over to any canisters and do any kind of functionality that you want. And then when you're ready, you can always bridge back to the Bitcoin network. So yeah, it is, CKBTC is a canister, or it's really a set of canisters, just a few, and I can show you those. And it follows the ICRC standard, ICRC 1 at least. I don't know if ICRC 2 is yet implemented for it, and ICRC standards are going to keep coming out. And so once a standard comes out, this, all the canisters out there need to take the time to actually upgrade to those standards. But it's at least ICRC 1 compliant, and we do have types for that, so I can show you that. So the CKBTC example, I think, is pretty good for helping you set up a complete local CKBTC setup. That might not be super, well, actually, I mean, if you're going to do minting and burning, then locally you do need to set all this up. If you just want to use CKBTC as an application and you're not going to mint and burn, you really don't need a lot of this. In fact, like from the front end even, you could just interact with the CKBTC canister. You could just call, as long as you have, build an agent up or whatever with the correct candid IDL stuff, then you could just call straight from the front end and have a user control things. But if you're going to do any kind of smart contract wallet or anything like that, then you'll want your own canister and you'll want to do the CKBTC transactions on behalf of your users. So if you want to do minting and burning, for example, the Bionic ordinals market that's going to be coming out, they have to deal with minting and burning, right? Because people are going to be sending either Bitcoin or ordinals over to wrap and everything. So, and the CKBTC part specifically is, I believe, how they're paying for everything. So I painstakingly went through this a few months ago to try to make it extremely clear how you can get all this stuff installed locally on your machine. Unfortunately, it was a very difficult process. Dfinity is working on a feature called DFX Poll that will make a ton of this way easier, because you'll be able to just say in your dfx.json what dependencies your canisters have. And as long as those canisters have DFX Poll functionality, then I believe on DFX Deploy or DFX Poll some command, you'll be able to run it and it will do all this manual work. It'll just do it for you. But at the time of building this, and I think even right now, you might still need to do this because I'm not sure if all canisters have been upgraded to DFX Poll. So that's what this README is doing. It is just going through, showing you how to install every one of the canisters that you would need to get a full CKBTC setup locally. So shows you how to install the CKBTC canister itself. I can show you the did file for that. Notice it's a bunch of ICRC1 methods with a few custom methods, right? So that's the CKBTC canister, and like I said, you can just call these methods from the front end if you want to. for the most basic functionality. Then there's the internet identity canister. You don't have to use internet identity, but it is one of the most popular ways to log into internet computer applications. So you need to get that set up if you want to use, I guess, internet identity as, I guess, kind of the front end wallet in a way. Then there's the know your transaction canister. So the internet computer, I guess the NNS decided that we should have a know your transaction canister or process on top of CKBTC using Chainalysis or other service providers to determine that Bitcoin coming in and possibly Bitcoin going out are clean according to those services. So the KYT canister provides that functionality. Yep. And then finally, you have the minter canister. And the minter canister will actually be able to receive Bitcoins and mint them. So, for example, get BTC address will generate an address that you can tell your users to send Bitcoin into. Update balance will actually do the minting process. There's things for estimating your fees and such. And then, yeah, going. So that was minting, and then I guess burning would be the other way, right? So that's what the minter is going to do. And then this is a very simple wallet. It's probably not the best wallet, but it shows you some basic stuff. For example, here's a basic front end. And yeah, it shows you how to log in with internet identity. And we create an agent to our backend canister. And then we can just call into our backend canister to get all the information that we want about that user and do things like transferring and such. Yep. And then finally, the actual backend itself. So this would be basically, if you're going to create a programmatic wallet, then you would want to create a backend like this inside of a canister, and you'd want to basically be an intermediary between your client and the actual CKBTC canister, because then you can provide functionality like, I don't know, social recovery and time locks and notifications and stuff like that. This doesn't show any of that. It's just basically a proxy, so it's not, I guess, super realistic in that way, but it shows you kind of what's going on. So notice we have an ICRC canister already implemented for you. So over time, we will update the ICRC canister to have more and more standards. So we definitely have all the ICRC1 standards, and we have ICRC2 as well, and there are more standards coming out. CKBTC, like I said, is only ICRC1. So if you call the ICRC2 methods on it, it's not going to work. Also, remember that CKBTC has these, which are not standard, right? So you'd have to create your own service to add those in. We don't have the full CKBTC ledger types for you right now. It just seemed, the CKBTC ledger, the ICP ledger, ICRC1 and 2, it seems kind of everything's up in the air and it's just a little bit complicated. So I guess we just haven't taken the time to fully put it together. And I don't know if they've even gotten that all figured out yet either. And then the minter, I think we created the minter ourselves. Yeah. And then these things are not that hard to do, right? So, for example, we don't provide the minter in ASL, but that's fine. You just make it yourself. You just, go to the did file, grab the methods that you need, and it's quite easy to just copy paste and then change the types to TypeScript. Candid and this API are actually quite similar. So I only needed these two methods, so I just grabbed them and I just made the types in here. Not too bad. So now I have my CKBTC and my minter. So then now it's just acting as a proxy. So if I want to get the balance of my user, then I will just call the CKBTC canister and pass in the me my canister is the owner, but I'm using the caller as the sub account. So this is allowing my canister to control everything programmatically for the user, but I can have as many sub accounts as I want. Update balance. This is after you have sent Bitcoin into the minter. I believe then you call update balance to get the CKBTC minted, basically. I believe that's how it works. And then getting the deposit address. Notice I'm on the minter asking for a BTC address. The owner is my canister because I'm a canister wallet. And the sub account is the caller, right? So this will get an address specifically for the user that is logged in. And finally, if I want to transfer, then I will transfer from the caller sub account and to in this case, this wallet only works right now within the wallet. So it's kind of like a PayPal or a Venmo. It's like everyone has to be using this wallet to send those transactions. So you just have to do it differently if you want to just be able to send to anybody. So it'll send from sub account to sub account with the owner always as this canister. And this is just standardized CRC1. And I had to do some manipulations apparently to get these things in the correct format. So that's basically all of it. Remember, reference 20.1. Bitcoin gives you links to most of these things. And then we have the Bitcoin example. We have the basic Bitcoin example. We have the CKBTC example. And you can always go to, and I highly recommend going to, the internetcomputer.org documentation. So happy to answer questions.
Yeah, so we have a few questions. Is it possible to use ECDSA signature to any services that use a signature scheme or any type of message to sign?
Can you repeat that?
I think the question is, can we do, if I understand correctly, can we do more than just Bitcoin things with ECDSA threshold signature?
You could do any ECDSA application. Yep,
So,
you notice the ECDSA APIs, there were two of them, generate the public key, or generate the key pair and sign. It has nothing to do with Bitcoin. It has nothing to do with Ethereum. It is just threshold ECDSA. So yeah, whatever, if your application calls for ECDSA and it's SecP 256K1, then it should work.
Yep. And there was another question. It's a bit off topic, but are there tools and methods to help with costing, estimation, forecast, security threat, safety? We did hear about audit service company. This seems important to me. So this will be the focus of the next session, actually. It will be about security. And yeah, we'll talk about the tools and the methods you can use. So there are some of them, it's pretty... I would say it's not as developed as probably other development environments, but you have some tools.
Yeah, I mean, yeah, we talked about, if you're talking about cost, like cycle cost, we talked about that in other lectures. You can use the performance counter and the instruction counter. And there are some benchmarking tools that Definitive has come out with as well. And for security, yep, we'll have a whole lecture on that in about an hour. And also for ASIL in particular, if you're using NPM dependencies or Rust plugins under the hood, then you'd want to make sure that you run NPM audit or cargo audit or whatever it is to, yeah, so, yep. And auditing is immature right now on the computer, but a code and state is working with auditors, and there are some options.
We're actually doing the first one at the moment. So we are auditing Sonic, it's NMM exchange. And so, well, I'm not really in the loop, but we have pretty good auditors on the line. Notably, we have the same person that designed the NNS. So he was working at Definity back then. So yeah, I think we'll learn a lot, and auditing is being developed, but it's pretty specific to IC environments. So I mean, we'll talk about it in 1 hour. There are some specification to take into account. Auditing, I don't understand the question, but yeah, not sure what you mean, Emmanuel. Oh yeah, there is a question. If we send to multiple addresses, do we just loop the send method, or is there a better way?
Are you talking about Bitcoin or CKBTC?
Can you precise, Mark? Both?
I don't know. I guess I don't understand the question, but if we go to Bitcoin and go to send, you have a Bitcoin transaction here. That's it. So this is the API. So if you could do what you want through the transaction, then you can do that. Is that your question? And then CKBTC just has the transfer method, right? It's just the ICRC1 transfer, which has these args. So you can go from one sub account to another account. So I don't see how you're able to send multiple from CKBTC, but if you can do that in a Bitcoin transaction, then I would assume it will work for Bitcoin. So if you could clarify, I could help more maybe.
Yeah. Any other question? Can you debit the transaction fee from the user who is making the Bitcoin transaction?
Can you do what with it from the user?
Can you debit the transaction fee from the user who is making a Bitcoin transaction? Essentially taking the transaction fee from the user instead of paying it from the service, I guess.
So for Bitcoin, yeah, the Bitcoin fee will be taken from the account, like the ECDSA key pair that you generate. The money to pay needs to be in that key pair. So automatically it is the user. And then CKBTC, it's all cycles, so it's already like that.
Yeah. Okay. Well, thank you, Jordan. We'll see us in 1 hour for the last lecture on security and best practices. So see you everyone.
See you guys.